Hello humans, my name is Professor Leach, and now that we have learned how to integrate even powers of cosine and odd powers of secants, we are ready to begin trigonometric substitution. Let's review the big plan for trigonometric substitution. So trigonometric substitution is a technique for integration in 3 acts. What it's for is integrating functions of x that involve usually square roots of unfactorable quadratics. They could be factorable. Square roots of quadratics. So f of x involves square roots of quadratics. That's usually what triggers a trigonometric substitution. So we look at f of x, we see that it involves square roots of quadratics, and that brings us to Act 1. So that's the, what's it called? The inciting incident. I can't remember. My storytelling basics. So we see that f of x involves square roots of quadratics, and trigonometric substitution is how we deal with that. So the first thing, Act 1, is we trade our x integral for a theta integral. We do the trigonometric substitution. We see our function, our integrand, involves square roots of quadratics. So we do a trigonometric substitution. This will give us an integral in terms of theta. So we do a trigonometric substitution. That will give us an integral in terms of theta. This integral is going to be a product of powers of trig functions. So g of theta will be a product of powers of trig functions. So g of theta is a product of powers of trig functions. That's what we just have been spending a lot of time integrating. So we kind of did Act 2 first. So Act 2, we integrate our product of powers of trig functions. If we can do this integration by substitution, we need to stop and go back to our f of x and look for the substitution that we could have done there. So that's why we wanted to really call out even powers of cosine and odd powers of secant, because that's what's going to show up in Act 2 mostly. Always exceptions in math there are. So then we integrate and we find an antiderivative in theta . But this is on our, so now we have the antiderivative in theta, but that's not what we want. So here's the antiderivative in theta. So capital G is the antiderivative in theta. So g of theta is an antiderivative in terms of theta, which is not what we want. So now we have to go back to x. So Act 3 is unsubstitute. And then that will get us back to get our antiderivative in x, which is what we were aiming for. So this is the trigonometric substitution game. Something tells us to do trigonometric substitution. That usually means that the function involves square roots of quadratics. Doesn't have to be square roots. It's mainly the quadratics thing. We do that so we can turn our f of x integral into a g of theta integral, which is a product of powers of trig functions, which we know how to deal with. But that's going to give us an antiderivative in terms of theta. So then we have to undo the trig substitution that we did. And it's more involved than just replacing the w with x squared plus 3x. So that's Act 3. We have to learn, those are the things that we have to learn how to do. We've already learned how to integrate. This integration is what we've been working on. This integration is where those even powers of cosine and odd powers of secant are going to show up that really confirm that this process was necessary. If we can do Act 2 with substitution, then we probably didn't have to do trigonometric substitution at all. So this is where we should expect to see even powers of cosine and odd powers of secant. Here you should expect to see even powers of cosine or odd powers of secant. And it's a little premature to point this out, but if you get to g of theta and say, I'm going to do substitution, stop. Go back to f of x and look for the substitution that you missed. If Act 2 can be completed with substitution, then stop, go back to f of x and look for the substitution that you missed. So these are just some things that we want to keep in mind going through this process. All right. So we've dealt with this Act 2, integrating products of powers of trig functions. That's what we spent the inordinate amount of time working on the last couple of days. We've been building up our integration skills. We've been building up our substitution skills. So it's more than just trying to do this trigonometric substitution. So today we want to talk about Act 1, how to do the trigonometric substitution. Let's talk about Act 1, how to do the trigonometric substitution. So this is this first leg of the journey, taking our f of x integral to a g of theta integral, getting to a product of powers of trig functions. There are 3 categories of trigonometric substitution that we have to learn. There are three cases of trigonometric substitution. There's the sine case. There is a tangent case. And there's a secant case. The sine case is where you see a quadratic of the form a squared minus x squared. The tangent case is when you see a quadratic of the form a squared plus x squared. The secant case is the other one, x squared minus a squared. In the sine case, here's the substitution that we make. In the sine case, we say that x is going to be a sine theta. We're going to use that x is a sine theta in the sine case. Now, remember when we're making a substitution in an integral, we have to substitute the dx as well. And so if x is a sine theta, then dx is a cosine theta. In the tangent case, if we see something that says a squared plus x squared, we're going to make the substitution x equals a tangent theta. Since we're doing an integration by substitution, we can't just leave the dx, we have to turn that into a theta as well. So dx will be a times secant squared theta, d theta. Forgot the dx on the d. Oops, d theta on the dx. Finally, in the secant case, you could probably guess, if it's x squared minus a squared, we're going to make the substitution x equals a secant theta, and that will require that dx is a secant theta, tangent theta, d theta. Now, this raises the question, but why though? How are we going to identify each of these three cases? We identify the three cases not because we memorize the cases or we just remember what the cases are supposed to be. We identify the case and we remember what substitution to make because we're going to understand why we're doing the trigonometric substitution. The reason that we're doing this is to put two terms into one term. We're trying to convert something with two terms in it to something with one term. Because we know square roots of two terms are trouble. Square root of a one term can be simplified. So the big idea is that the square root of two terms is trouble. Square root of one term is no problem. So the big idea is the square root of two terms is trouble. Square root of one term is no problem. But the square root of two terms is trouble. If I have something that says the square root of a squared minus x squared, that's messy. But if it was just the square root of, say, w squared, I get to just write w. So that's good. That's progress. So keep in mind, what we're trying to fix is we have a square root of two terms. What's going to happen? So the sine case, is for a squared minus x squared. When I make the substitution a sine theta, this turns into a squared minus a squared sine squared theta. And that's all just going to be a squared cosine squared. So let's see what, how easy it's going to be to remember which case is which. This part of the summary, I want to reinforce that we're making a substitution for x, and that means we have to substitute the dx as well. Let's turn the page and reinforce why it's going to be so easy to remember which case is which. So let's suppose that we have a squared minus x squared. And let's further suppose that we're going to make the substitution x equals a sine theta. This is also going to require that dx is a cosine theta, but we're focused on the why are we doing this business. So x squared is going to be replaced with a sine theta. So this is going to look like a squared minus a sine theta squared. A sine theta, the square of the product of a and the sine of theta, is going to look like a squared minus a squared sine squared theta. You know what? I'm just going to have to, I messed up the coloring on this one. What we can do here is factor out the a squared, and that's going to leave a 1 minus sine squared theta. And 1 minus sine squared theta is cosine squared theta. That is the point of this process. And that is how we will remember which case is which. So a squared minus x squared in the substituted integral will be a squared cosine squared. We've gone from 2 terms to 1 term. 2 terms enter, 1 term leaves. It's just Thunderdome. So that'll help us remember each of the 3 cases. The other case, because I did them out of order, would be a squared plus x squared. So this we know is the tangent case. So we'd make the substitution x equals a tangent theta. Plugging that in, we get a squared plus a tangent theta squared. So that's going to say a squared plus a squared tangent squared theta. And we can once again factor out the a squared, and that leaves us with 1 plus tangent theta, tangent squared theta. And 1 plus tangent squared is secant squared. 2 terms enter, 1 term leaves. Trig sub Thunderdome. The final form was the secant case. So the secant case is when the x squared is positive and the a squared is negative. And we're going to do the same thing we did in the other 2 cases, just with a different trig function. X is a secant theta. So I'm going to have a secant theta squared. So that gives us a squared secant squared theta minus a squared. Factor out the a squared, and that leaves us with a secant squared theta minus 1. And so we get a squared times tangent squared. This is the trigonometric substitution Thunderdome. 2 terms enter, 1 term leaves. It's in theta, but it's 1 term. If I had to take the square root of a squared minus x squared, I'm now that I can't distribute the exponent over the sum, but I can take the square root of a squared cosine squared and just write a cosine. So the point is, two terms enter. One term leaves.
Professor.
Every time I think of it turning two terms into one term, I always think of Thunderdome, and I don't think anybody has seen that movie anymore. So if you haven't seen Mad Max Beyond Thunderdome, don't. I don't think it's really necessary. Usually when I come across a movie that I keep referring to, I'm like, oh yeah, you got to go see that movie. Like if it's Office Space, y'all got to go see Office Space, even though it's a really old movie. It's like your future because you want to be engineers and stuff. So let's see this in context. See, one person has seen it because they know Master Blaster runs Bartertown. So for example, let's suppose that we wanted to integrate the square roots of 4. I always use 4. Let's use 9 this time. 9 minus x squared to x. Let's run a trigonometric substitution on this. We see this square root of a 9 minus x squared. So if I put this on like a test or a quiz or a homework or a final exam, some of you will just try to say, oh, I'll just make that 3 minus x. Yeah. Some of you will distribute the exponent over the sum, which is funny. But you should know that you don't get 0 out of 4 points for that. You get negative 4 points out of 4 for that. Because that's a mistake that you just can't be making anymore. Yeah, I mean, you just got to learn to read, man. So the square root of 9 minus x squared, the form is a squared minus x squared, and so that makes us think of sine. That 9 minus x squared is going to become a 9 cosine squared. So we're going to make our substitution. Sorry, not W. We're doing trig sub. X equals 3 sine theta. We're in an integral now, so dx is going to be 3 cosine theta d theta. So this becomes the integral of the square root of 9 minus 3 sine theta squared. The dx is going to be a 3 cosine theta d theta. Where we got the trig sub, where we got the idea to do the trig sub, this 9 minus x squared, that's where the thing happens. That's where our Pythagorean identity shows up. So this is all 9 minus 9 sine squared theta, which is all just 9 cosine squared theta. So the next thing that happens is a Pythagorean identity. It's important to remember this step because this is the whole point of doing a trigonometric substitution, for this 9 minus x squared to get transformed into a 9 cosine squared theta. So this is the integral of the square roots of 9 cosine squared theta and we still have this times 3 cosine theta d theta. Now we can see why this is useful, because the square root of 9 cosine squared theta is just 3 cosine theta. So this 9 cosine, square root of 9 cosine squared theta, we got two things out of this. First of all, we had a square root of 2 terms, which is always trouble. But now we've got the square root of 1 term, which we can simplify. So now our integral is, let's see, we have a 9 times the integral of cosine squared theta. We have completed Act 1. After this, we would integrate the cosine squared. So after this is the stuff that we've already talked about. Any questions? All right. So let's see. Let's suppose that this was the other way around. If this is a square root of x squared minus 9. I'm not going to do the second half because we just did the second act. I'm not going to do Act 2 because we just did Act 2. And we don't know how to do Act 3 yet. We need some practice on Act 1. Then we'll learn how to do Act 3, how to get back from our substitution. And then we can put it all together in an entire problem. So let's suppose that we wanted to integrate a very similar thing, x squared minus 9 to x. So the x squared is positive and the a squared is negative. So that tells us to use the secant case of a trigonometric substitution. So we're going to make the substitution x equals 3 secant theta. We can't just substitute the x, we also have to substitute the dx. So we take the derivative, dx. The derivative of secant theta is secant theta tangent theta d theta. Now we make the substitution. This is going to be a square root of 3 secant theta squared minus 9. And then the dx gets replaced with 3 secant theta tangent theta d theta. Inside the radical, the thing that we expect to happen happens. The Pythagorean identity comes along and replaces a secant squared minus 1 with tangent squared. That was the point of doing this substitution. So 9 secant squared theta minus 9 is 9 tangent squared theta. That was the point of this exercise. That is why we are doing a trigonometric substitution in the first place, because it makes this happen. So now our integral is the square root of 9 tangent squared sorry, 9 tangent squared theta times 3 secant theta tangent theta d theta. So now we can simplify the square root of 9 tangent squared to 3 tangent. because now we have the square root of one term, not two terms. And so I have in total a 9 out in front. I have an integral of secant times tangent squared. Which, because the tangent is even and the secant is odd, is just going to be a sum of odd powers of secant. Tangent squared is secant squared minus 1. So our integral is going to be a secant cubed minus a secant. So we get, as expected, a bunch of odd powers of secant. This is where we have completed Act 1. We know the integral of secant cubed. We know the integral of secant, so we're ready to proceed on to Act 2. This is where Act 1 is complete. Act 2 would be the integrating of the even power of cosine or the odd powers of secant. And then Act 3, which we don't know how to do yet, is going to be getting back from theta to x, getting from theta back to x. Substitution, by the way, is the only time we should be going back to the x. Otherwise, it's an x for a reason. But in substitution, it's what you started with, so you kind of have to.
Professor, can I ask
Not all math lessons are life lessons. Any questions?
Yeah, Professor. Just point of clarification. On the second line of the integral underneath 3 secant theta.
Right. So what you need to remember is what the three cases are. A squared minus x squared, a squared plus x squared minus a squared. You have to remember that there's a sine, a tangent, and a secant case. The more important thing is you have to remember why we are doing this. The whole point of doing this trigonometric substitution process is to get from two terms to one term with a Pythagorean identity. Oh, I might be on, my computer's on mute. Hang on. What's your question?
Yeah, sorry. I wanted to ask for the back down to the secant problem.
Yeah.
Where it was minus 9. So 9 secant squared theta minus 9. Was that, what happened to that minus 9?
We factored the 9 out, and that left it with a secant squared minus 1. Secant squared minus 1 is equal to tangent.
Oh, okay. Thank you. So it doesn't multiply by 9, it just gets factored out and then falls off?
Nothing falls off. Secant squared minus 1 is equal to tangent. That's a Pythagorean identity, like sine squared plus cosine squared equals 1.
Okay.
So it's the same reason that up here, when we had 9 minus 9 sine squared, you factor out the 9, and that leaves a 1 minus sine squared. And 1 minus sine squared is equal to cosine squared. Don't think of it as something falling off and then magical transformations. It's not magic. 1 minus sine squared can be replaced with cosine squared. And all that's happening down here is that secant squared minus 1 is replaced with tangent squared. Any questions? All right. So you've got to remember in trigonometric substitution. You got to remember what the point is. And the whole point is using these Pythagorean identities to go from two terms down to one term. Yeah, I didn't have my headphones on today, and then my computer was on mute, so I wasn't able to hear. Sorry about that. All right. So it seems like a lot to remember, but that's only because it's a lot to remember. And you have to remember all of it, all the time, with perfect accuracy. So no problem there. We'll have a lot more we'll have some more practice on Act 1. The most important thing is to remember the 3 cases and to remember why you're doing this in the first place. Now tomorrow we can talk about how Act 3 is supposed to work. How we get, once we integrate things, we'll have an antiderivative in terms of theta. How do we get back from theta to an antiderivative in x? Apart from that, I believe that's it. I'm done. Email this to your grandma and I'll see you some other time.